Hi again everyone. In this video we're going to continue our look at infinite series, and this particular video is a simple example involving the so-called comparison theorem or the comparison test. Okay, now there are two parts to the comparison test, and this is just a real simple version of it. So firstly, consider some given infinite series where the a sub n's are non-negative. Okay, the first part to the comparison theorem or comparison test is this. If we can construct a convergent series, sigma bn, such that the a n's up here are less than or equal to the b n's here for each n, then the original series also converges. And conversely, the second part is, if we can construct a divergent series, sigma bn, such that this inequality holds, then the original series also diverges. Okay, so let's look at the following simple example. Here we're given a series and we're asked to discuss the convergence or divergence of the series. Now, notice there's two parts to this theorem, and when you apply the theorem, it's not always obvious which one you're trying to apply. I mean, you can't apply both of them, all right? But usually we use simple inequalities on this a sub n, and it tends to be clear which one you're aiming for. Okay, so the basic idea is to apply some simple inequalities. And the question is, well, what kind of inequalities are we going to use here? And that inequality will come up with something like this or something like this. Right, so let's look at log n. Okay, so what simple inequalities do we know for log n? Well, a simple inequality is the following. Log n is less than or equal to n for all n greater than or equal to 1. So what we can do with this simple inequality is come up with some inequality for 1 on log n just by rearranging. Okay, so I'm going to rearrange and come up with this. Okay, so from this inequality, you can hopefully see now that, well, do we have this or this? This is my a n, remember. So it looks like we've got this inequality. And now all we want to see is, does the series associated with 1 on n, is it divergent? If it is divergent, then we can apply this second part of the comparison theorem. Note that having this kind of inequality rules out the first part because we don't have this. Okay? So if I let Bn be 1 on n, and we want to know, does this diverge? Well, it's a power series, 1 on n to the p, the sigma, with power equal to 1. It's a divergent power series. Okay, now the power is equal to 1, and these type of series are convergent when the power is strictly greater than 1 and divergent otherwise. So yes, this new series that we've constructed is divergent. So if we go back to the second part of our comparison theorem, we have constructed a divergent series, sigma 1 on n, such that 1 on n is less than or equal to 1 on log n for all n. And then we can conclude that our original series must diverge. So our series up here must diverge. So by the comparison test or the comparison theorem, we conclude that our original series diverges. Okay, so we've named our tests, we've made a conclusion, and I said at the beginning of this video that this is just a simple version. Firstly, you don't need these inequalities holding for all n. Okay, all you really need is these inequalities holding for little n large enough. Okay, so here we had them holding for n greater than or equal to 1. All right, so just reviewing the comparison theorem, there's two parts. You can generally decide on which one you're aiming for via simple inequalities, and they should set you down the right road. And then you need to show that the original series, the constructed series converges or diverges depending on which conclusion you want here, or you're aiming for.